Hi guys, today we are going to be looking at Video-LLaMA 2. This paper is a continuation of a previous paper that we looked at this channel. So for those who are new to the channel, this channel is currently going through a bunch of pivotal research papers in VLMs, LLMs and in general because of a paper reading group I'm a part of. So in today's video, we are going to be looking at Video-LLaMA 2, how this model builds upon the previous model spatial-temporal understanding, and how it is a better video transformer for related tasks. So first, looking at the motivation to have this model, the first version of the model struggled with detailed spatial and temporal model in video content. Basically, the model wasn't able to understand rather detailed question answers that were dealing with both audio and the video in the actual video. The first model also struggled a lot with long sequence tasks, meaning that it wasn't really able to process more than 8 frames and quickly lost context, interest and accuracy when it was subjected to more than 8 frames. One more motivation that they have for this new model is that there are way more datasets available in the current day and age for video transformer training. When they first trained the model, this is one issue that they faced, which is a serious lack of dataset to train upon. That is a video dataset which has audio and annotated as well. So they are utilizing the new datasets to address more use cases and push the state-of-the-art performance. So how are they introducing, what are they introducing to meet these motivations, and how are they achieving this? Basically, they are employing a similar dual branch framework, which has an audio and visual language branch. For the spatial temporal understanding, however, they are going to be using a spatial temporal convolutional character. This is one major improvement from the previous queue former and a video queue former method that they were kind of using for compiling features from different video frames. So they are using an STC connector for a more efficient video token generation. And finally, for the language model that is at the end of the training, they are using Mistral, Mixtral, 8x7B and Quen 2. So all of this is done in multi-stage training. So we'll be taking a look at how the architecture works, how the training happened, what are the results, and what can you do with these models. So first, looking at the architecture is following a 2-branch architecture, much like the first one, which has video language layer and an audio language layer, which is finally feeding into a pre-trained language model. Now, first looking at the architecture's vision language or the vision transformer branch, a video is first divided into different frames. These frames are then going to be passed through the vision encoder, which is the clip vision encoder in this case. This visual encoder will be taking in the images in the aspect ratio 336 and 336, which they have achieved by either resizing or padding all the images that they are taking from the datasets. The way the model works, it creates about 24 into 24 tokens. That is 576 tokens because of the fixed 14 into 14 patch size the model is able to take for ingestion. And finally, this visual encoder is going to be producing detailed feature for each of the frames that will be passed further onto the STC connector. Now, STC connector is what is most important in this model, so we are going to be looking at it. First, the video frames that have passed through the visual encoder are going to enter the STC connector, where in the first layer, each of the frames are individually seen and each of the patches are kind of used to form a interaction between the other patches. For example, a certain patch which has the kitten, it is gonna be mapping the relative position of the kitten next to the chick. So it is gonna do that for all of the frames. Moving on to spatial temporal aggregation, this step, what it's gonna do is basically aggregate both the spatial awareness, that is in relation to the time, how did the chick move to the cat or how did the cat move to the chick, but also while reducing the time it took to have a more aggregated version. And finally, it is gonna feed into a spatial interaction convolutional layer, which is again gonna look at all these different parameters and comparisons that they have and inferred from the temporal and spatial comparisons of different frames to feed it into a flattening layer. Now, all that sounded very difficult, right? So let's try to understand it in a more technical sense, which makes more sense with numbers. So the whole point of introducing STC Connector is to address the limitations of QFormer. QFormer was taking in temporal information, but rather because of the weird video encoding plus temporal projection layer, it wasn't really able to generate good results. So some of the limitations of the QFormer based architecture from the first model were they wanted to address maintaining the spatial and temporal order in output visual tokens. They wanted to reduce the number of spatial temporal tokens, and they also wanted to alleviate the information loss during space time downsampling. Now, these three issues, when you look at it, is kind of being dealt with the STC connector. So first, looking at the maintaining spatial temporal order in the output visual tokens, that is having an understanding of both space, time, and the tokens in the final output. It is gonna be doing that by the first reg stage, where already the batch and the time is being introduced into the pipeline. It is one of the parameters that is being fed forward with the visual encoding. This, as you remember, 24 into 24 patches were being sent forward, so we have 576 patches. 1024 is a target token that we are putting for the language model to have. So as you can see over here, while maintaining the spatial temporal order in the output visual tokens, for the output visual tokens, we have the number of batches that we are taking, we have the time that we are having. 1024 is the final token count that we are trying to get out of the image. So it is all conserving all these parameters about the individual frames by assigning them a variable. Moving on to reducing the number of spatial temporal tokens, it is doing that by spatially aggregating the 3D convolutional layer. What we saw earlier in the form of the second step, where multiple frames are being used to condense information about the spatial and the temporal changes of different entities in the image, we are gonna be doing that by this spatial aggregation 3D convolutional layer. As you can see on the right, it is basically looking across the frames, combining the information. It is a way more condensed information. It is a way more smaller information. The 576 tokens that we had over here would go to 36. The time that we were looking at would go to t by 4. So we have already reduced the amount of time and the space variables. Now, finally, when we look at the second reg stage block, where we are trying to refine the compressed information that we have, we are going to be passing it through something similar than the first layer, where it is calculating a loss on the basis of interaction with the immediate neighbors. This step should refine the compressed information further, and the final projection, the final output that is sent to the projection layer over here, the final output that is sent to the flattening layer is being taken from this final reg stage block, which is a richer token, having preserved the spatial and temporal performance of the entire video and the model. So the dimension for this would look something like batch into time by 4 into 36 into 1024, where time has reduced quite a bit. The video patch tokens have also reduced quite a bit, and that means we have way more condensed information to be fed into this 1024 tokens, which means that the information is going to be more accurate. Now, looking at the audio language branch, the audio processing is being done by taking raw audio, converting them into F-bank spectrograms, For those who don't understand a lot about sound wave dynamics, you can think of them as basic screenshots of the audio, which is being the audio is being represented as a wave. So these spectrograms are passed through the audio encoder, which is the beats encoder. We'll be talking a bit about it just in a second. This beats encoder is creating detailed audio features pass, and which are being passed to the flattening layer, which is finally going to be combining all the audio tokens in one feature vector, push it to the projection layer and send it to the LLM. Now leave all that aside. What's more important is to understand how this audio encoder is working, because apart from the audio encoder, this audio language branch is pretty simple. It is just flattening out the final tokens and refining them for the language model. So when we look at the audio encoder, that's a beat audio encoder, one good thing about this model is that it uses less data, is more efficient. It is able to take raw audio and converts them to spectrograms, which is a way easier way to look at images. It takes random projections from the spectrograms and uses them for an iterative learning. How it does so is by masking parts of the projection, parts of the audio, parts of the spectrogram, and it will try to predict the masked part of the audio with the audio context that it has from the other unmasked parts. So that it keeps on retraining on this particular practice. It repeats for better results, and that's where we are subjected with a model that is pretty strong. The model, as you can see on the right, is being compared to a lot of these other audio models. Some of them which you may have heard about is audio MAE, WAV to VEC, that's wave to vector. And in all of these parameters, it is performing rather well. But you can see there's a serious lack of models in this category, where most of these models are coming back from 21-22. So yeah, there is a huge scope of new models being trained in this particular sphere. Now, moving back to the topic, this beats encoder is basically going to give a rather good representation of the audio while understanding the temporal dynamics of it, because it has been trained to predict things depending on the neighbors. It has been trained to look at the entire picture first with masks all over the place, but learn how to figure out what is behind those masks. That's why the model is going to be performing rather well. Looking at the training, the first major part of the training is the vision branch. The vision branch is being trained in two parts. First is the pre-training, and second is going to be the fine-tuning. When we are looking at the alright, so the vision encoder and the language model are frozen as the STC connector is being trained. Now this particular step is done so that the architecture is able to understand the relationship between the video encodings and the language encodings better. It is being done to bridge the gap in the visual language branch. This particular part of the training uses both image and video data. As you can see on the bottom, it is using Panda 70 million, WebVid, VDAL internal vid, CC3M DCI, a total of 103 million samples, from which they have used 12.2 million samples. These samples are greatly helping with the model understanding the different relationship between objects and their corresponding words. So all this is being done with the training objective to minimize the cross entropy of the next token, the cross entropy loss of the next token. Okay, looking at the vision branches fine-tuning aspect, we see that the visual encoder is frozen while we try to optimize the language model and the STC. This is done so because clip model is quite good at understanding images, so it doesn't really need a lot of training. Also, secondly, this final fine-tuning is being done for the model's prowess and Q&A tasks to be increased. That's why the STC connector and the language model are being trained to form more deeper, more complex queries from the same images. So this is done through high quality multimodal annotations for fine-tuning. The training object still remains the same, minimizing the cross entropy loss for the next tokens. The dataset it takes is a mix of video text data, image text data, and pure text data. Pure text data would be a data that is asking it to solve a bunch of normal question and answering questions. It's not a difficult data set, but rather the video image text data sets are much more interesting because you can see that the VQA data sets and the instruction data sets are rather huge, which are going to be giving the model a rather big advantage on these Q&A tasks. When we look at the audio branch, for the pre-training, the audio encoder and the LLM are frozen, similar to how in the visual language branch, while they try to understanding the bridging encoding between them. The training objective is to minimize the next token prediction loss for the text. They have used the WAV caps 400k dataset. You can see a sample of the dataset down below. Data would be having raw descriptions about the audio which has been written by a human, and on the basis of those raw descriptions from those videos, ChatGPT is being asked to answer some particular question. So that's how the dataset looks like. That's what they are training the model to be able to do. They're training the model to be able to answer questions like how ChatGPT is over here. Like, for example, looking at the second sample where they're talking about timber and wood, ripsaw, carpenter's workshop, motor car, Ford Escort 1300. I don't really need to know all that. The video description should probably say something like someone is using a ripsaw in a carpenter's workshop. A car is passing with its horn. That's a rather simple understanding, and that's all I need to know. So that's what they are trying to do over here in the pre-training, giving the model the ability to generalize better on different type of audio it is subjected to. Once they have that, they have fine-tuned the model to enhance the versatility of the model on multitask learning. The LLM layer is frozen, the audio encoder and the audio projection is optimized. The training objective remains the same, and it is subjected to a bunch of Q&A data sets. So that's where a bunch of the other part of the training happens for the audio branch. And finally, one other thing that they are doing differently from the first model is training both the models together in an audio video joint training, where only the visual encoder is frozen while the projections, STC, audio and LLMs are all optimized. The audio tracks are aligned with video clips. The sampling data for each batch is in 2:1 ratio of audio visual data to visual data to audio data. Now, for the audio video joint training, they have used a bunch of technical data sets like AVQA music, VGG sound, Evol, Instruct, Video Chat, Next QA, and they have used a bunch of creative data sets like Urban, Sound QA, Clotho, and Lava. So that's where they are training the model to be able to answer more creative answers and also for more technical answers. Now let's look at the different implementations that the model and the research paper presents. As I had mentioned earlier, the model is using Mistral 7P, Mixtral, Quen 2 and a bunch of these models. So what they are basically just different implementations of the model that they have introduced in the paper. The visual encoder is being changed between clip large and siglip. The audio encoder remains same. That's the beats encoder. And finally, for the language decoder, they have been using Mistral 7B Instruct, Mixtral 8x7B Instruct, Quen 2 72B, Quen 2 72B. Yeah, when we look at performance of the model on various tasks, we look at some tasks that show global scene understanding, where the model is able to understand that the bot is dancing in front of a group of arcade machines. It is able to understand some of the creative aspects, some of the more abstract aspects of the movement, which are like you can see in the second part of the sentence, where it says the boy's movements and the setting gives off a joyful and playful vibe, where it is coming up with a bunch of creative answers. The second very interesting example that they have shared is a spatial-temporal and awareness example. By the way, you will see all of these frames are 8 frames. That's what they are feeding the model right now. That's why this video looks like this. this is how the video encoder is gonna be looking at the videos. So yeah, I know you may lost a lot of context between the frames, but that's why that's one of the problem statements. It's an open-ended problem statements for this particular task. Now, this particular task example, spatial temporal awareness, you can see that the model is able to tell that the yellow cab turns left at the intersection, which is quite an interesting thing, because it was able to understand the temporal and spatial position of the car, the head of the car, where it was going and where it might have taken a turn, which is rather interesting and impressive. Common reasoning tasks being simple. Where do you think, why do you think it is a morning or night? It is saying that it is morning depending on the light and the coffee that the girl is drinking over here. And finally, there's one more special temporal fine grained understanding, where you can see that the model is operating as an OCR, but in a time setting where the actual note whose text they were asking to decipher was introduced in the video later. So it is able to say that. So when we look at the results of the model on different tasks, I still feel like these numbers are a bit too close for us to actually see a difference, but I think the Video-LLaMA is generating rather good results and captions. So some of the models that they are comparing this model with are proprietary models and open source models. Proprietary, which it kind of beats, is Gemini 1 Pro, Gemini Ultra, GPT-4V, which are all huge models. When we look at the open-end VQA section, the results don't really change that much. GPT-4V, GPT-4o are still performing better, though that is something which is kind of understandable, because the Video-LLaMA model is being trained on an older GPT's generated dataset. The performance of the model on open-ended audio QA can be seen over here, where the model, even though trained on much less hours of the audio, is generating way better results. Quen audio, for example, Quen models are very closely compared with the Mistral model, so it's good to see that a Mistral based model is performing better than a Quen based model over here. When we look at the performance of the model on the overall task of open-ended audio video QA, there are much less options to compare the model with, some of them being one LLM, Video-LLaMA, X-Instruct Blip. One of them, which is very interesting, is one llama, because it is using a training of 1007 million pairs. Even after that, the model has funnily low Q&A performance on the music Q&A dataset. We can see Video-LLaMA over here with 7 billion parameters was able to get a way better performance on the dataset. And yeah, so I would love to hear what you guys think about Video-LLaMA 2, what you would think that is where the direction of video LLMs is going, what is some possible ideas we can collaborate, and you can let me know if you want to collaborate on creating a video transformer of our own. And I'll see you next week. Until then, keep your models fed and your code bug free.